So in this video, we're going to be revising waves. Very simple. Before we do, however, syllabus update again, because 2023. Now, in 2023, they didn't remove anything from waves. They just added a few things. Sure, it's not written here in the overall things, except this. It says electromagnetic spectrum, addition of learning objectives concerning communication, but you'll find out that this is a lot larger than what you expect compared to the original curriculum. This is why. First, this is all stuff we know when it comes to lenses. You know what a lens is, what's the focal point, focal length, principal focus. We're going to revise this stuff anyway, but that has not changed. The only thing that has changed is this when it comes to lenses. It's the addition of describing the diverging lens, like understanding what is a diverging lens and how we can use it to correct short and long-sightedness. So sightedness. So folks like me who use glasses, well, glass gang for the win. There's a reason why we wear glasses. Like it has to do with our own lenses in our eyes, but that's another story. Additionally, this is the part that they added for communication for core students, which isn't really much. Satellites use microwaves. That's it. So there's a difference between low orbit and geostationary orbits, but that's the same thing. They both use microwave. This is the new stuff that you extended students need to know. What type of waves do you use for mobile phones, for Bluetooth, for optical fibers? What's the difference between digital and analog? And here's the thing. If you watch the electricity chapter, you know that digital and analog, which is digital electronics, has been removed from the syllabus, but they basically shifted the concepts of digital analog from electricity to waves here. So digital analog still exists, as their definitions are still there. And we need to know that sound is capable of being transmitted as digital and analog, and we'll talk about their advantages. So this is all new stuff. Then, finally, core students, please note, if you see this, especially at the top of the page, this is not for you, but please do listen. It'll help you round out your understanding of physics. And if you see it right next to an equation, that equation will not be used by you at all. And let's get started. Wait, what are we starting? Where's the content? Well, before we start with the content, like what are we studying today, we need to ask a question. What's a wave? The answer, it's a transfer of energy. That's it. It's a method of transferring energy, primarily through vibrations. So for example, I'm talking right now. I'm emitting sound waves, or actually, I am producing, look at me, beautiful, aren't I? See, this is what I look like. Anyway, or should we call this guy OG gang, Mr. U? Anyway, so when Mr. U starts to talk, it produces energy, sound energy, and that sound energy gets transferred through the vibration of the air molecules, producing a sound wave. So the purpose of energy of a wave is to transfer energy, whatever the type, light energy, heat, kinetic, whatever the sound. So very good. Next, so what are we talking about? First, we'll talk about the different types of waves: transverse, longitudinal, electromagnetic, and mechanical. What are the properties that we measure in a wave? So it's amplitude, wavelength, period, and frequency and stuff. The electromagnetic spectrum. So what are the different types of waves that we have that are all electromagnetic besides the spectrum of light, besides Roy Gebiv? The general behavior of waves, reflection, refraction, and diffraction, because they both apply to light and sound. So we're going to apply them to sound waves first, and then to light waves. When it comes to light, we'll focus on two things: the refraction of light and the reflection of light when it comes to mirrors, and the refraction of light when it comes to lenses, and how we can use lenses to correct vision. Next, let's talk about types. We have 4 types. The first 2 types are called mechanical and electromagnetic. These 2 are opposites. We basically ask you, hey, does this wave need a medium or not? So a mechanical wave is a wave that needs a medium, but electromagnetic waves do not need a medium. So we need to answer a question. What do we mean by medium? A medium means matter. So the solid or liquid or gas that the wave is going to go through. The wave is going to go through something and the molecules are going to vibrate. It's called mechanical. For example, you have sound waves, water waves, or ripple waves. These are all mechanical waves because they need matter to go through. They cannot travel through empty space. They cannot travel through a vacuum. Electromagnetic waves, on the other hand, like light and infrared and ultraviolet and gamma rays and whatnot, these are all waves that are able to travel through a vacuum because they do not need particles. In other words, they do not vibrate particles. They vibrate something else, to be honest. Like there is some form of vibration in the form of electric and magnetic fields, but it's not particles that are vibrating. And since particles are not vibrating, they don't need them, which means the sun is emitting ultraviolet rays or infrared or light. They can all travel through space or a vacuum because they're electromagnetic, because they don't need a medium. So mechanical waves like sound cannot travel through a vacuum. That's why, you know, the famous saying, nobody can hear you scream in space, because you know what, sound waves are mechanical. Next, the other two types of waves are also opposites, and they're called transverse and longitudinal. These have to do with how molecules vibrate. These have to do with how molecules vibrate. A transverse wave is where the molecules vibrate perpendicular to wave motion, meaning if you have a single molecule here, this molecule vibrates up and then down. Up, follow the cursor, and then down. You can see that. Up. So if you notice, a single molecule doesn't move from its place. It's just vibrating up and down. But because the other molecules are also vibrating up and down in order, because they're vibrating up and down in a certain order or sequence, they create this illusion of something moving. Well, technically, something is moving to the right. What is moving to the right is the energy, which is the wave. But the molecules are vibrating up and down, producing what we call crests, which is the upper peaks, and troughs, which are the lower peaks. This is basically all waves, by the way, except for sound waves. I'm kind of spoiling it right now, but sound waves are what we call longitudinal waves. This is where the molecules do not vibrate up and down or perpendicular to the direction of wave motion. They vibrate forwards and backwards. They vibrate forwards and backwards. So if you look at a single molecule here, take a look at this red dot, focus on it a bit. Let's see if we can zoom into this just a second. Whoop-a-doo-doo. It's not going to move as long as you zoomed in, but this little dot over here, it's going to be moving left and right. It's not going to be moving up and down. And this, instead of creating crests and troughs, this creates regions where the molecules are close to each other, which we call a compression. And it creates regions where the molecules are far apart, called a rarefaction. So you have compressions and rarefaction. Obviously, these are animated pictures and such, GIFs. But if you're just drawing the waves yourself, this is how we draw a transverse wave. It's nothing special. You have crests and troughs. This is how we represent longitudinal waves. We draw multiple lines close to each other, then a few lines far apart, then a few lines close to each other, a few lines far apart. This represents a compression. All of this represents a rarefaction. Crest and trough, you know the drill. Yeah, I did say sound waves are the only longitudinal waves, but there is actually one more type of longitudinal wave. When it comes to earthquakes, when there's an earthquake underground due to the vibration and collision of the tectonic plates of the outer crust of the crust, what happens is the following: the earth starts to vibrate. The surface vibrates up and down, right? We call them S waves because they're on the surface. And these are transverse. But the rocks or the ground itself, underground, does not vibrate up and down. It vibrates forward and backwards, creating what we call a P wave. P is short for pressure wave. They used to call it a pressure wave before defining it as longitudinal. So during an earthquake, you have two types of waves. Waves on the surface, which break your buildings and breaks the ground. These are called S waves. And waves underground called P waves. These are longitudinal. Very good. Let's look at properties. There are 5 properties that we need to measure. Amplitude and wavelength are the distances. Period and frequency are related to time. And finally, their speed. Amplitude is defined as the maximum displacement of the molecules from the mean position. What's the mean position? The center line of a wave. This is called the mean position. The word mean means average. So center position, original position, they're all fine. The distance that the molecules move up or down is called displacement. The maximum displacement, this is called amplitude. Maximum displacement is called amplitude. All right? This represents the amount of energy in a wave. So the more energy a wave has, the greater the amplitude. The less energy a wave has, the smaller the amplitude. Wavelength is defined as the distance between 2 successive crests or 2 successive troughs. Literally from its name, it's the length of a wave. It's how long one wave is. If a wave starts at a crest, then the distance from one crest to the next, that's called the wavelength. And this is the symbol, it's called lambda. The distance from trough to the next trough is also called lambda, the wavelength. But a wave, or a single wave, is not only defined by the distance from a crest to a crest or a trough to a trough. Realistically, you can start from the center as well. If you go up to the crest, down to the trough, then back up to the crest, to the center of the wave again, like if you start at the center and you end in the center after touching a crest and a trough, this is also considered one wavelength. So the wavelength is not just from crest to crest or trough to trough. On a diagram, it's also from the center, not to the one right next to it, to the other. That's one complete wave or oscillation. When it comes to longitudinal waves, they don't have crests and troughs, so we measure it from a compression to the next compression, or from a rarefaction to the next rarefaction. But because you have so many different lines in a wave like this, you have to choose the center, or just choose the same line, but I prefer to choose the center of the compression. So this is wavelength, or the center of the rarefaction to the next center. That's the wavelength. Very good. Next, what is period then? Period is defined as the time taken. It's defined as the time taken for one complete oscillation. Time for one complete oscillation. It's just time. So when a wave moves from crest to crest, the time that it takes for you to see one crest to the next, that's called period. If I go back for a second to this animation, and let's draw a line right here. If I were to start a stopwatch, let me pull out a stopwatch, give me a second, and stopwatch. And I'll wait until the wave hits this line and start. And 1, 2, 3, 4, stop. It took 4.14 seconds for one wave to go through. That's what we call the period. Kind of also why there's no diagram for it, because it's literally a time that you measure. Frequency, on the other hand, is defined as the number of oscillations. You could also say waves per unit time or per second. So how many waves pass by you per second? The unit of measurement of frequency is called hertz, Hz. So for example, if I tell you that a wave has a frequency of 10 hertz, this means that it completes 10 oscillations per second. finishes 10 oscillations per second. Now, there is an equation that relates period and frequency. They're inversely proportional. Because if you think about it, the higher the frequency of a wave, the lower the period. It takes less time. And also the lower the wavelength, by the way, the shorter the wavelength will be. But if you have a wave with a very low frequency, meaning the number of oscillations has decreased, the wavelength and the period increases. So it takes more time to finish one complete oscillation. And obviously it travels longer in one complete oscillation. So we simply say that frequency and period are inversely proportional, or F equals 1 over T, where T is not just any time, T is the time of one oscillation. As always, remember to hydrate. Gosh, I'll preach this forever. And I'll still forget to drink water myself. Anyway, finally, how do we calculate speed? Now, we know that speed is distance over time. That's not an issue. Speed is distance over time. But in a wave, we don't really measure the total distance and the total time. Instead, we measure the distance of one oscillation and the time for one oscillation. So we simply say that speed is lambda over t, wavelength over time. However, with a little bit of, smart maths, remember that F equals 1 over t, a little bit of substitution, you can remove the 1 over t and replace that with F. So you can say F times lambda. So you change the over t to lambda, you substitute. So the equation that we use to calculate the speed of a wave is V equals F times lambda, right? Frequency times wavelength. For a quick example, let's say you're given a wave with a frequency of 10 hertz. And you know that the speed of this wave is 300 meters per second. Calculate the wavelength. See, this time I didn't ask you to calculate the speed. I'm actually asking to calculate the wavelength. It doesn't matter. You're given the frequency, you're given the speed, you can calculate lambda very easily. Lambda equals V over F. So rearrange this formula. The speed is 300, the frequency is 10. 300 over 10 gives you 30 meters. It's a very long wave, by the way, which makes sense. It's a very small frequency. 10 oscillations a second is actually a very low frequency. Next. Now, this is where most of the new stuff regarding waves has, shown up in the syllabus. We already talked about what electromagnetic waves are. An electromagnetic wave is a wave that does not need a medium to propagate or to travel through. It can travel through a vacuum. But it's not just light that's electromagnetic. You have a ton of electromagnetic waves, and they're all listed in front of you right now. Before we discuss them individually, they all have the same speed. They all have the same speed. And they're all transverse. There's no such thing as a longitudinal electromagnetic wave. They all have the same speed. They're all transverse. You have to memorize this value, though. 3 times 10 power 8, which is about 300 million meters per second. It's very fast. Honestly, there's nothing faster than the speed of light in air. Right? Very good. Now, before I talk about these, there are a few questions, so let's go over them. Remember to type your questions in chat, guys. Year 10, we don't need to memorize equations, right? No, you have to. With Cambridge, specifically, you have to memorize all of the equations. Please. Like, he does give a formula sheet, and we'll discuss this during the problem-solving section, so we'll see what the exams are like, and he does give you a formula sheet, but it's a very, very, very anemic formula sheet. It barely has anything useful. So yes, please, that's part of the difficulty of this subject. You have to memorize formulas. All right. So when you say this equation, do you mean the speed equation? This is only for year 10 students, not for year 9, all right? This is only for extended students, not for core students. Oh, this is not an equation. This is a value of speed, and you have to memorize it. You have to memorize 3 times 10 power 8. He's not going to ask you what type of equation. It's more along the question. It's more along the lines of, hey, what's the speed of light in air? It's 3 times 10 power 8. Here's the tricky one. What's the speed of radio waves in the air? 3 times 10 power 8. That's the trick. They all have the same speed in the air. You're welcome. So moving on. So what are the different types of electromagnetic waves that we have? And why are they ordered this way? Because they're ordered in terms of frequency. As you go to the right, the frequency increases. So this has the highest frequency. The other side is the lowest frequency. Earlier, we mentioned that frequency and wavelength are inversely proportional. So as the frequency increases, the wavelength decreases, and vice versa. If the frequency decreases, the wavelength will increase. How do we memorize them? Well, I always like to start in the middle of the table. If you have visible light, which consists of 7 different colors, they are red, orange, yellow, green, blue, indigo, and violet, or Roy Gibev. Roy Gibev. You want to pronounce it Roy Gibev, Roy Gibev, it doesn't matter. Just try to remember that. And remember, red has the lowest frequency. Violet has the longest frequency, highest frequency. If you go higher than violet, you end up with ultraviolet. And keep that in mind. The word ultra means greater than. So when I say ultraviolet, I mean it's a wave with a frequency higher than violets, right after violets. Following ultraviolets, you have X-rays, and then you have gamma rays. It kind of looks like UV, X, and Y, but I digress. If you go even lower than red, however, you end up with infrared. Again, the word infra means below. So infrared means less than red or below red. Then you have microwaves, and then you have radio waves. Very good. You need to memorize these in order of their frequency and wavelengths. The only one that's visible is light. Everything else is invisible. Yeah. Let's briefly discuss some of their applications, because you need to remember some of the applications for each individual type of wave. And here's a quick table. Remember to snapshot it if you need it. Or you'll find it in your notes or summaries. Gamma rays. Let's start from the highest. What are they used for? Mainly to treat cancer, or to sterilize medical equipment or food and such. What are X-rays used for? To check for broken bones. So if I put my hand, for example, my arm in an X-ray machine, the X-rays work, or like help me see if my bones are broken, because they're absorbed by materials that are very dense, but they can go through less dense objects. So my bones are very dense. X-rays cannot go through my bones. Like imagine this. Here's a bone in my arm. I know I'm an artist by nature, but please do not envy me. Someday you'll be able to draw amazing art such as mine. Assume this is my arm now. If I break my arm, X-rays cannot go through a bone, or they barely go through, but they can go through my fracture, because they can go through my flesh and everything else. So the reason why X-rays work is that they cannot pass through the bones or more dense objects, but they can pass through your flesh or any cracks or such. We also use it when it comes to security checks at airports, when you want to check if you have any metallic objects in your luggage. So if I have a pistol or anything else in my luggage, you should be able to. I'm sorry if I'm laughing, because somebody sent me a very funny message. I'll share it in a bit, but anyway. If I have a pistol or a knife or any kind of dangerous metallic object in my bag, you don't have to open my bag to find out what's inside. X-rays just go through, they're stopped by the metallic objects, and you can see them on the screen. Ultraviolet rays come primarily from the sun, right? It has a lot of applications, but the primary thing is my body uses it for what? To produce vitamin D. Sure, you can use it to check for fake banknotes and sterilize water and such like that, but your body needs it to produce vitamin D. We don't need to discuss what we use light for. Infrared waves. Now, they're very wide-ranging. First, we discussed infrared waves earlier when we talked about thermal physics, so they transfer heat. But it's also used for remote controls, TV remotes and air conditioner remote controls. It's also used for intruder alarms and thermal imaging. So think of it this way. You're in a museum, you have cameras that see light, show you pictures, but then you have these infrared cameras that show heat signatures. That's how they can detect if somebody's in a room, even though it might be dark and there's no light. And we can also use it to transfer information using optical fibers. All right. Microwaves, primarily used for satellite television, mobile phones, and a certain frequency is used for microwave ovens, but it's primarily used for these two. Radio waves are used for, again, radios, obviously, right? RFID tags, like NFC, like stuff on your phone when you tap a card or something to your phone, it triggers something, that works. But it's mainly communication. Now, what are the dangers or hazards? Microwaves, and I don't mean all microwaves. I don't mean the microwaves from your phone. I mean microwaves that are used in a microwave oven. They can be used to internally heat your cells, boil you on the inside. Infrared waves, again, the certain frequencies that actually heat things, they can cause you skin damage or burns. They can literally burn you. Ultraviolet rays. Now, remember, your body needs it for vitamin D. Too much of a good thing is a bad thing. So too much ultraviolet radiation exposure could cause skin cancer. X-rays and gamma rays are both what we call ionizing radiation, which means when they go through cells and atoms, they remove electrons from those atoms, causing them to ionize, and that could cause damage to cells. So how do we protect ourselves in general? You stay away from them, from the source, reduce your exposure time as much as possible, and maybe use a shield or a barrier to protect yourself from, right? Yeah, this is for extended folks. What do we mainly use electromagnetic waves for when it comes to communication, though, specifically? Like we said, your phone and Wi-Fi, they all use microwaves. They can go through walls. You don't need very large receiving equipment to detect or to emit or receive microwaves. So we use it for Wi-Fi and phones. Bluetooth, Bluetooth headset and stuff. This isn't a Bluetooth headset itself or earphones. They use radio waves, right? Optical fibers, what do they use? Infrared waves or visible light. So the optic fibers that are in the ground, we'll talk about them in a bit. Optic fibers that transfer information for internet use and so on, they use infrared waves and visible light to transfer information. We already mentioned satellites. They use microwaves, right? Regardless of whether it's a low orbit satellite or a geostationary satellite, it doesn't matter. We use microwaves for it. One more thing. There are two types of signals when it comes to transferring information, called analog and digital. For example, you have sound waves. Sound waves can be transmitted as either analog or digital. But what do I mean by analog or digital? Their definitions are literally signals are just continuous values, whereas digital have fixed values. Again, what does that physically mean to us? Right now, I'm speaking to you, right? You can hear my voice. Got a lot of inflection and different types of sounds that I'm emitting, and I can raise my voice, lower my voice, and so on. My voice is not something constant. It changes. that's considered an analog signal. It doesn't have a fixed value. It keeps fluctuating all the time depending on the signal. Whereas a digital signal has fixed values. It's either high or low. Think of a sound wave that sounds like a beep, like beep. That's a fixed signal. That doesn't change, right? So it's either on or off. When it comes to transmitting information, you can transmit it as analog signals. Like you can take the current or the voltage that's going to be going through. That's going to be going through a wave and transmit it as a digital signal or analog. But digital is so much better. Why? Because here's the problem. Any wave as it travels gets weaker and it loses energy. If an analog signal loses energy, it's very hard to regenerate it or amplify it. It's hard to make it louder because what happens when it gets weaker is that it gets affected by other waves and it gathers what we call noise. When you regenerate it to make the signal stronger by just adding a little bit more energy to the wave, it ends up adding some noise to it. So, it sounds terrible. If it's a sound, it's like listening to a song on a radio with the antenna missing, and you got all this static in the music, all of that random noise as you're listening to the song. It's terrible. Digital signals are so much better. Why? Because it's only one of two values. It's like high or low, higher, low, higher, low, higher, low. It's very easy to transfer this information. Like circuits are literally designed for digital things like high and low. So it's very fast when it comes to this transfer. Second, even if this signal gets weaker over time, like, oh my God, no, this signal is weak. This is still low. This signal is weak. This is still low. Signal is weak. We know what this value should be. It's very easy to put a regenerator or an amplifier, and it just immediately gives me the exact same signal again because there's no continuous variation. Noise doesn't affect it. So we say that digital is better than analog because one, it increases the rate of transmission, like how fast you're transferring this information, and increases the range of it, as in how far it can travel. Because even if it loses energy, it isn't affected by noise very much, and therefore it's easier to amplify or regenerate. Nice one. Extended focus is one way to call someone tall. Then what should I call not so tall people? Not so extended focus? Anyway, let's move on. Let's talk about the behavior of waves. There are three types of behavior. Unextended. Unextended, nice one. There are three types of behavior that you need to keep in mind. We call them reflection, refraction, and diffraction. So three types of behavior. All waves exhibit this behavior. Light waves, sound waves, water waves, everything. So you just need to understand the basic concept of these behaviors, and then we'll apply them to sound and light. Before we do, when we draw waves, you have to understand what the term wavefront means. Instead of drawing a transverse wave like this with crests and troughs, instead we draw the wave as if we're looking at it from above. So we draw an arrow that is called the ray. This represents the direction of the wave. And then we just draw straight lines where the crests are supposed to be. We call these straight lines wave fronts. The whole point of this drawing method or system, the whole point of this is to simplify my diagram so I don't have to waste my time drawing crests and troughs and ruining things, and to show me what happens to the wave itself. Does the wavelength increase? Does the wavelength decrease? Because the distance between two successive wave fronts is the wavelength. Because if this is a crest and this is a crest, the distance between them is lambda, the wavelength. It'll also show us what happens to the shape of the wave. Does it bend? Does it curve? Does it stay straight? So what is reflection? It's the change in direction of wave when it hits the surface. It's refraction. It's change in speed. It's not change in direction, it's change in speed when a medium changes, but it can cause the direction to change. What is diffraction? It's the spreading of a wave when it goes through a gap or around an edge or a corner. So one behavior is when a wave hits something and then comes back. It's called reflection. Another is when a wave travels from one medium to another. So it changes speed and it can also bend. That's also fine. And diffraction is when a wave spreads out because it goes through an opening or a gap. So reflection, a wave that's going to hit this surface. This could be a solid surface. This could be a water wave. This could be a light wave. This could be a sound wave. Anyway, this ray that's going to hit the surface is called the incident ray. This is called the incident ray. When it hits the surface, it reflects. So the ray that comes back is called the reflected ray. That's great. Nice. Incident and reflected. Reflection only follows one simple rule, which is what? Which is that the angle of incidence, I, is equal to the angle of reflection, R. But what are these, you mister? Well, the angle between the incident ray and the normal, this is called I, angle of incidence. And the angle between the reflected ray and the normal is called R. Now that you've heard that properly, your question might be, what's the normal? It's just an imaginary line. You can draw it dotted, you can draw it solid, doesn't matter. It's just an imaginary line that's at 90 degrees to the surface, to the mirror that's doing the reflection. That's why it's called normal. In mathematics, the word normal means perpendicular, not normal as in regular. So the angle between the angle of the incident ray and the normal, that's called the angle of incidence. The angle between the reflected ray and the normal is called the angle of reflection. Easy peasy. Finally, the wave fronts of the wave. Nothing about them changes, just their direction. They're always, wave fronts are always perpendicular to their ray. So if a wave is going up, they're also going up with it. If a wave is going down, it's going down with it. But the wavelength doesn't change, the speed doesn't change, the frequency does not change, nothing changes, just the direction. All right. Then what is refraction? Refraction is when a wave changes its speed as it travels from one medium to another. For example, this is deep water. This is deep water. And this is shallow water. When water waves travel from deep to shallow, the speed decreases. For water waves, this change in medium, this change in depth is a change in medium. If a sound is traveling through the air and goes into water, that changes the speed. If light is traveling through the air and goes through glass, that changes the speed. For water waves, and just for now, we're talking about water waves. When a wave moves from deep to shallow, the speed goes from high to low. The speed decreases. And it's not just the speed that decreases. Take a look. Here's the wavelength. Now here's the wavelength. The wavelength also decreases. We call the shallow water a more dense medium. So the speed decreases and the wavelength decreases. We call deep water a less dense medium. This has nothing to do with density, which is mass over volume. It's just a figure of speech. It's just like me saying, hey, this medium is heavy and this medium is light. So if you're going through a heavy medium, you're going to move slowly. If it's going through a light medium, you're going to move quickly. All right? Good. Very good. Now you're going to have to memorize, you're just going to have to memorize what mediums change which waves. We only have 3 waves that you have to remember: water waves, sound waves, and light waves. So for water waves, as you just saw, they travel faster in deep water, but slower in shallow water. Before I move on, frequency is always constant. I don't care what anyone says. The frequency does not change during refraction. All right. We're not going to go over why. What shallow water is a more dense medium. Just memorize it as is, because we're just trying to revise everything as quickly as possible. But you can think of it this way. Oh, fine. You can think of it this way. There's less water for the molecules to vibrate up and down. So the water molecules find it harder to vibrate up and down and transfer the energy to the neighboring molecules. So they slow down the transfer of energy. The more space the molecules have to vibrate up and down, the faster they can transfer the energy. You could think of it that way. It kind of helps. Amplitude is not something we often discuss. That's another question. The question was, what about the amplitude? Amplitude is not something we will often discuss, because if you see the amplitude decreasing, the wave has simply lost energy. Is the wave losing energy because of refraction or not? That's not our concern. But if you see the amplitude decreasing, it has lost energy. That's the simple answer. Now, refraction does not only change the speed, it also changes the direction. If a wave or a ray is moving from less dense to more dense and it's perpendicular to the surface, it does not change direction. But if the wave hits the surface at an angle, it does change direction. It does not keep moving in a straight line. Instead, it bends, the ray bends closer to the norm. And vice versa. If a wave is moving from a more dense medium to a less dense medium, it doesn't move in the same direction. It bends away from the norm. The question is why? That's because before the wave hits that, surface, the entire wave is moving at the same speed. But at a certain point, part of the wave is still in the less dense medium, so it's moving more quickly. The other part is in the more dense medium, so it's moving more slowly. So the entire wave ends up bending a bit because part of it is slower than the other. And as you can see here, the wavelength decreases. Why? Because the speed decreases. Same thing. The wavelength here has increased. Why? Because the speed has increased. You have to memorize the change in direction. Next. Why did it skip? Okay. Diffraction. That's the last behavior. Diffraction is defined as a spreading of a wave as it goes through a gap. Meaning, if these are your wavefronts and it hits a barrier, a wall essentially, and that barrier has a gap in it, an opening, this is the gap that we're talking about, the wave will not continue moving with the same size of the gap. No. The moment it goes through the gap, sure, it takes the size of the gap, but then the wavefront itself starts getting longer and longer and longer. In other words, it spreads. It doesn't stay at the same size of the gap, it just spreads and spreads and spreads. But the amount of spreading, like how much does it spread by, depends on the wavelength and how big this gap is. When the gap is very large, or the wavelength is very small, meaning the gap is greater than the size of the wavelength, there is very little diffraction. There is very little spreading. But if you make the gap smaller, or the wavelength larger, like they're almost equal, or the gap is a bit smaller than the wavelength, like it's not like an absolute thing. It's not large and small. It's if you gradually keep decreasing it, what's going to happen is that this wave will now change its shape and it'll curve more and more and more. It's like you took the wavefront and you squished it so it bends and starts to curve outwards. So the smaller the gap, the more the wave diffracts. And the larger the gap, the less the wave diffracts. Less diffraction. This is more diffraction. So any questions before we move on? The sound waves and light waves and everything else? All right, let's move on. So what are sound waves? So-called sound waves. What are sound waves? Sound waves are basically mechanical and longitudinal waves. They're both mechanical and longitudinal waves because they need a medium and the molecules vibrate forward and backwards, producing compressions and rarefactions. Easy. But sound waves don't just, produce compressions and rarefactions. They also change the pressure of the air or the atmosphere. Also change the pressure of the atmosphere. During a compression, because the molecules are super close to each other, the pressure of the atmosphere increases. During a rarefaction, because the molecules are all far apart, the pressure of the molecules decreases. Why? Because the closer you push the molecules together, the more frequently they collide with each other. So the pressure increases. And the farther apart the molecules are, the less frequently they collide with each other. So the pressure decreases. This is why if you draw a graph of how the pressure of the atmosphere changes with the distance traveled by the wave, you will see a waveform similar to the transverse wave. But these aren't crests and troughs. These are compressions and rarefactions. Because a compression is a region where the pressure is higher than atmospheric, and the rarefaction is a region where the pressure is lower than atmospheric. Right? Good. Yeah. Sound waves have speed. What's the speed of sound? In air, the speed of sound is around 330 meters per second to around 350 meters per second. That's the range. In liquids, the speed is around 1,500 meters per second. It's actually about 900 to 2,000, but that's the middle of it. In steel, it's around 5,000 meters per second. So around 3,000 to 10,000. It's a bit faster in solids than liquids and faster in liquids than gases. Why? Because solid molecules are already very close to each other, whereas gas molecules are far apart. So it's a lot easier to transfer molecules that vibrate forward and backwards when they're already touching each other. But if the molecules are far apart, it takes more time. So therefore, the sound travels a lot slower in air compared to liquids and solids. By the way, it's not slow by any account. Like by our standards, 330 meters per second is still very fast. It's just slow relative to liquids and solids. Like I said, you're going to have to memorize how speeds change for different waves. So for water waves, it was the depth of the water. For sound waves, it's the material, but moving from solid to liquid to gas, the speed decreases. It's fastest in solids and slowest in gases. If you want to measure the speed of sound, it's very simple. Although it's not a very accurate experiment, but you can get two people, one of them with something like a starting pistol or anything that produces both light and sound, a flash and a sound. And somebody else should have a stopwatch. And then you measure the distance between the two of you, the measuring tape. If you are the one with the pistol and you fire the pistol, the second person sees the flash first. So he presses start on the stopwatch, start. And then a few moments later, he hears the sound. So he presses stop. So he gets the time taken. It's the time taken for the sound to travel to him. This is all assuming that light travels instantly. Like it doesn't. Somebody commented saying he won't hear the sound, he's already dead. No. It's a starting pistol. It's a pistol that just produces flash of sound, flash of light and some smoke and some sound. No bullets, huh? Who taught you to be so gruesome? Oh, it was me. Anyway. So we assume that light travels in zero time. That's why we can do this. And just like you said, lightning and thunder. You see the lightning first, because we had a lightning storm last night. It was beautiful. You see the lightning first, like the sky lights up, and then a few moments later, you hear the sound, right? Definitely, they should get an A star for thinking outside the box. Okay, moving on. Amplitude affects the loudness of the sound. So when I raise my voice, or I raise the volume, or you raise the volume, of this video or this recording or whatever it is on your phone, you raise the volume, you're actually increasing the amplitude of the sound. When you decrease the volume, you're decreasing the amplitude. So a large amplitude is a very loud sound. A small amplitude is a very quiet sound. Next, frequency affects the pitch of the sound, how high-pitched or how low-pitched it is, and they're proportional. So a high frequency wave has a very high pitch. So it's a very sharp, shrill sound. Think like a banshee screaming or something. If you don't know what a banshee is, just, I don't know, play a video game or two, or like watch a horror movie or two. And if you have a low frequency wave, it has a low pitch. So think something like an opera singer. Oh, deep voice. We human beings don't hear everything though. We can only hear from 20 to 20,000 hertz or 20 kilohertz. This is called the range of audible frequencies. Anything less than 20 is called an infra sound, just like infrared, but this time it's infrasound. Anything higher than 20,000 is called an ultra sound. Very good. Finally, what about echoes? An echo is just a reflection of sound. So just applying reflection, the sound moves. If you're on a, let's say you got stranded on an island or something, and you shout because for some reason you knocked your boat off of that island, you emit a sound. Hello, or help, or I'm hungry, anything. When that sound hits this cliff, the other island, and it reflects back, maybe that's the mainland, this reflection is called an echo. This reflection is called an echo. An echo is just the reflection of sound. When hit the surface, came back. What you need to be wary of when it comes to echo questions is the concept of distance. Why? Let's say you are 300 meters. Yeah, 300 meters away from this other island, from this surface. And I tell you that the speed of sound is something that you have to memorize, is 330 meters per second. As an example, can you find the time taken for you to hear the echo? Of course you can. If I say speed is distance over time, this means time is distance over speed. What's the distance? 300. No, wait. The distance traveled by the sound to produce the echo is 300 meters to the wall, and then it came back another 300 meters, so it reflected back. So that's 300 to the wall, 300 from the wall. You actually travel a distance of 600, so it's 300 times 2. Over 330. So this gives me 600 divided by 330, which gives us a time of 1.8 seconds, which makes sense. Like 1.8 seconds is pretty decent, a pretty decent time to be able to measure quickly. Very good. So that's the one thing I want you to be careful of when it comes to solving echo questions. And that is the distance traveled by the echo is back and forth. But the distance between you and the surface is half of that distance, half of the back and forth. We have a question here. What's the difference between pitch and speed? Pitch is how sharp or deep a sound is. It's the type of sound that you hear. Is it like a low, very beep, or a very sharp beep? Right? So it's like the tone of the sound. Speed is just how fast it travels. Doesn't really affect what you hear. How fast does it travel from point A to point B? Yeah. Light waves. What is a light wave? It's an electromagnetic and transverse wave. We said that all electromagnetic waves are transverse. But we're going to study a few things in particular. First, let's talk about the refraction of light. If I give you a glass block, for light waves, glass is considered a more dense medium, whereas air is considered a less dense medium. In other words, light travels much faster in air than it does in glass, which makes sense. If a ray of light hits the surface of this glass block at 90 degrees, it does not bend. It just continues straight. No bending. Why? Because if it's perpendicular to the surface, it doesn't bend. It slows down, sure. The speed of light in air is around 3 times 10 power 8. The speed of light in glass is going to be around 2 times 10 power 8. This is a number that you don't have to memorize, but chances are you'll eventually memorize it because most of the questions involving the speed of light in glass give you this as an answer or as a value. But if the light is moving from air to glass at an angle, you have another story. First, some of the light reflects. We call this partial reflection. But most of the light refracts, bends closer to the normal. That's fine. You draw a normal here, then bends away from the normal again. So bends towards the normal, bends away from the normal. This is refraction. But turns out there's a funny thing when it comes to the values of that change in speed and angle. If this angle was around 30 degrees, this is going to be approximately 20 degrees. It's actually 19.5 degrees, but still. If the angle here is 20 degrees, it goes back to 30. In other words, the ray that's incident on the glass block is parallel to the ray that leaves because the surfaces are parallel to each other. Because the surfaces are parallel to each other. All right? Good. Speaking of which, this is extended, okay? There's a ratio that you have to memorize, which is the ratio of the speed of light in air over the speed of light in glass. It is also the ratio of the angles. So when the speed changed from 3 to 2 and then back to 3, the angles also changed with roughly the same ratio. With roughly the same ratio. Oh, if you want to, there's a question. Can you specify the angle of refraction? Here it is. Or this is also an angle of refraction outside of the block R. This is an angle of incidence. This is an angle of incidence. The ratio of the speeds is the same as the ratio of the angles. So n is equal to speed of light in air over speed of light in the medium or the glass. Let's solve this as a quick example. If n equals speed of light in air, this is something we memorize, 3 times 10 power 8, over speed of light in glass, which was given in the previous page, 2 times 10 power 8. This gives you an n of 1.5. An n of 1.5 literally translates to this, that the speed of light in the air is 1.5 times faster than the speed of light in the medium, in the glass, for example. It just tells you how dense that medium is. The larger the value of n, the slower the speed will be in the glass block. Okay. Then, next. What about the index? What is this refractive index when it comes to the angles? It's the same thing. It's the same thing. It's just the ratio of sine the angle in air over sine the angle in glass. So as a follow-up question, I can say, hey, sorry. The angle of incidence in the air in the previous question was 50 degrees. So you've got light incident on a glass surface at 50 degrees. If the n is 1.5, just like we calculated, find the angle of refraction, which is find the angle here inside the glass. So it's quite simple. N equals sine angle in air over sine angle in the glass. So n is 1.5, which is equal to sine 50 over sine r. So sine r is equal to sine 50 over 1.5. This gives us, let me plug these numbers in, 0.51. Amazing. No, not done. If you want the angle r, you have to remove the sine. So you shift sine, the answer that you get, sine to the power of. This gives you an r of 30.7 degrees or 31 degrees. Which is correct, by the way, because the angle should decrease. If you're moving from air to glass, it should bend closer to the norm. Yes, this is only for extended steel. Very good. Yeah. One more thing. There's one special thing that does happen when light travels from glass to air. This is very important. If light is traveling from glass to air, meaning if you have a ray of light that's incident on this glass block at 90 degrees and it hits the center, this ray of light will bend away from the norm. Like it won't be here. It'll just simply bend away from the normal. And this is fine. But then, if this angle increases a bit, this angle must increase. Like it has to bend even further away from the norm. Because you can't just keep increasing this and the external ray doesn't change. No, it has to move with it. So if we increase, this ray will continue to increase in angle until it eventually almost touches the glass surface. So it was refracting normally so far until it almost touches the glass surface. This angle is called the critical angle of incidence. And this is around 42 degrees. It depends on the material, and we'll see how we can find it in a bit. But this angle is called the critical angle. It's the angle of incidence inside glass, like when light is moving from glass to air, that causes the angle of refraction in the air to become 90. So again, what is the critical angle? It is the angle of incidence in glass, or if the light is moving from glass to air, that causes the angle of refraction to be 90. Very good. The more important thing is what happens if you increase the angle of incidence even beyond this. Like, what if you go even more? Well, the ray of light has already extended past this, it can't move any further unless it goes inside the glass, and it does. If the angle of incidence is greater than the critical angle, then the light will simply reflect. Light will simply reflect. This occurs when the angle of incidence is greater than the critical angle. And this is called total internal reflection. So again, what is total internal reflection? It's the complete reflection of light inside a glass block, like when it's moving from glass to air. When it's moving from glass to air, that causes the light ray to completely reflect within the glass. It acts like a mirror. The glass surface acts like a mirror. But this has one condition. The angle of incidence has to be greater than critical, greater than 42, 45, 46, 50, 55. And it follows the laws of reflection just as fine. Angle of incidence equals angle of reflection, no big deal. All right? Yeah. How do we find this critical angle? Like if I tell you, for example, that, hey, you have a light ray here, it touches the surface as it leaves. You know that this angle is 90. You know that this angle is 90. Then what's the angle inside? It's called the critical angle. I don't know what the critical is, but I do know that the angle of refraction in the air is 90 and that the value of n of this material is 1.5. We got it through some other means, whether we measure different angles or speed, it doesn't matter. If the n is 1.5 and you want to find out the critical angle, this is the formula that we use. N is equal to 1 over sine c. Technically, this is actually n equals sine 90, which is the angle in air, over sine c, which is the critical angle. But sine 90 gives you 1. N is called the refractive index. Don't forget, this is the same formula as before. N equals sine air over sine glass, speed over speed. So N is the refractive index, which is equal to sine 90 over sine c. So N equals 1 over sine c. So if I want c, I'll say sine c equals 1 over n, which is 1 over 1.5. And remember, you're going to have to shift sign your answer. So 1 divided by 1.5, shift sign the answer. This gives me value of c of 41.8 degrees, which is almost 42. Again, you don't have to memorize 42. You just have to memorize this thing over here. N equals 1 over sine c. Again, N is the refractive index. N is the refractive index. Don't forget it. A lot of you keep forgetting what N means. N is the refractive index, which is just the ratio of the speeds or the angles, which shows you how dense the material is optically when it comes to light. Is this clear? Any other questions? All right, good. Fine, let's talk about dispersion of light. This is when white light splits and stuff. But wait, what if you don't have white light? What if you have what we call monochromatic light? Monochromatic means light of one frequency or a single frequency. I can't even say one color, even though the word chroma means color, but I can't say one color because actually the color red, for example, has multiple frequencies. So when I say monochromatic, I mean one specific frequency. As the light moves from air to glass, it bends closer to the normal, and then it bends away from the normal. And that's fine. This is just regular refraction. The dispersion happens if you get white light. Why? Because white light consists of 7 different colors, and each color has a different frequency and a different wavelength. So each color has a different index, as in each color will refract by a different amount. So when you have a ray of white light, it splits because every color refracts. This is still refraction, by the way. This is nothing special. This is still refraction. It's just that every color has a different angle of refraction and it slows down differently. So each color bends with a different angle. Red is the color that bends the least because it has the lowest frequency. Whereas violet is the color that bends the most because it has the highest frequency. The higher the frequency of a wave, the more it slows down inside the medium, by the way. And the smaller the frequency of a wave, the less it slows down inside the medium. As for why, let's not get into it, to be honest. It's irrelevant to our discussion today. So if you pass white light through a prism, it splits into the 7 different colors. Roy, Gibev. Above red, you still have infrared, assuming the source emits infrared waves. Or below violet, you have, or above violet, meaning you have ultraviolet. Because it has a higher frequency than violet, so in the region below. And that is dispersion. This is still called refraction, by the way. Like the bending is still called refraction. Dispersion is only when the light splits, right? Good. And this is what it basically looks like. White light shining through. You get your spectrum, Roy, Gibev. You can tell, by the way, that, you know, violet isn't really purple. It's just a very, very dark shade of blue. Let's talk about reflection. So what is reflection? Reflection is when light hits a surface and comes back. Cool. But if you're standing in front of a mirror, you end up seeing what we call an image. You end up seeing what we call an image. This image is considered a virtual image. It is not real. In other words, it cannot be seen on a screen. It's not actual light being emitted from the mirror. The mirror is just reflecting the light, so it makes you think that there's an image behind it when there isn't. There's a difference between a virtual image, which is an image that you cannot see on a screen, and a real image, which you're looking at right now. You're looking at the screen, whether it's your phone, your laptop, your TV, whatever this is that you're looking at right now. This is an image that's in front of you on the screen, but it's called a real image because the image comes directly from the screen itself. The light is from the screen itself. It's not the light hitting a surface reflecting to my eyes, and it makes me think the light comes from the mirror. There are different properties. The images are the same size, same distance from the mirror. They're upright, and they're not upside down. And they're laterally inverted, meaning the right side becomes the left side, and the left side becomes the right side. So this is actually the right of the image. This is the left of the image. This is his right hand. This is his left hand, and vice versa. Yeah. How do we draw? Question: is every human who looks into a mirror hallucinating? Absolutely. Yes. Exactly. We're all crazy. Yeah. How do we draw a ray diagram for a mirror? Let me just show you the shortcut. Since we know that the image is supposed to be behind the mirror and at the same distance from the object to the mirror, what we do is this: we measure the distance here between the object and the mirror. Then we take that same distance behind the mirror and we mark the image. I'm just showing you a method which I use to cheat and get this answer very quickly, not the actual diagram. Let's erase this. So the first thing you do is you draw where the image is supposed to be. If this is the object, this is where the image will be. Same distance and same position. Then draw any two light rays from the diagram, from the object to the mirror. I don't care. Draw a normal here because light is supposed to hit the surface and reflect. The light is supposed to hit the surface and reflect. And then from the image, draw a line to this point and extend it. Draw a line from the image to this point and extend it. You don't even need a protractor. This diagram will be almost 100% accurate. You don't need to draw the reflections accurately because this will draw the reflections accurately for you. So again, step one, we mark where the image is. It's the same distance between it and the object, between the image and the mirror. I'm sorry, the object and the mirror, image and the mirror. All right. So yes, the question will literally ask you, hey, draw a ray diagram to find the position of the image. So like I said, we're cheating. We're marking the image first. After we mark the image, we draw these rays. And then from the image, we draw two more rays, or the actual two rays passing through the mirror itself, where it reflects. Good. And this is what it looks like if you've drawn it properly. Finally, then, this is the last thing we'll discuss for tonight. And with this, we'll finish Unit 3. Let's talk about lenses. And I mean lenses like the ones I'm wearing. They're just pieces of glass that are shaped a certain way. Some of them are thin from the edges and thick in the middle, called convex lenses, like so. And some of them are thick from the ends, but thin in the middle. This is called a concave lens or a diverging lens. First, let's talk about converging lenses, or what we call convex lenses. The whole idea of a convex or a converging lens is that if light rays are parallel to each other as they strike the lens, the light rays will bend due to refraction. This is just regular refraction. Due to refraction, they will bend. But because of the shape of the lens, they all pass through the same point before moving forward along their way. This point where they meet is called the focal point. This is the point where if light rays are parallel to each other, like from the sun, hit the lens, they will pass through that focal point. If you do this with sunlight, you can focus sunlight and burn stuff, but that's not our focus for today. If you take an object that's emitting light and you have it pass light through a lens, the light rays will focus. The light rays will focus somewhere in the air, because you know that's the focal point, and then create an image on a screen for us. Then create a big image on the screen for us. This image will always be inverted, because if you take a look at this diagram, the light rays from the top of the object or hitting the top of the lens go down, and the light rays hitting the bottom of the lens go up. So the image itself gets flipped over. Not to mention, this is a real image. Why? Because the light is literally on a screen. It's not just a reflection off of a mirror. It's actually light on a screen. Yeah. One more thing. There's just one more thing here. Something I need to point out. Let's clear this. The distance, let me clear this stuff first. The distance between the center of the lens and our focal point is called the focal length, or the focal distance. And there are always two focal points for a lens, one on the left and one on the right. Because lenses are symmetrical, it doesn't matter which side the light decides to go through, it depends on us. So it will focus and produce images either way. Yeah. How do we draw the ray diagram? Follow my steps very closely before I show you the final results for any case you have. Step number one, draw a ray from the top of the object that's horizontal and strikes the middle of the lens. Step number two, it needs to go through the focal point. Now you might be wondering, where's the focal point, you mister? He didn't tell me. Well, he will either mark it for you, or he will tell you, for example, that the focal length or the distance is 2 centimeters, for example. And every 1 square on this diagram is 1 centimeter. So from the center of the lens, You count 2 centimeters, so that's 1 and 2, and you mark that as your focal. So he will either mark it for you, which is what he'll do most of the time, or he'll just draw a focal point. Like he'll give you, sorry, the focal length, and you find that. So ray number 1, from the top of the object, which is the arrow over here, from the top of the object, draw a horizontal line until it hits the center of the lens, and then from the center of the lens, have it pass through focal point. To where? To infinity and beyond. Buzz Lightyear style. Step number 2, we need a second ray to intersect with the first ray in order to produce an image. You have 2 options. The first option is to pass through from the top of the object through the center of the lens, perfectly through the center. And that will continue without bending. If you've drawn this correctly, they should intersect here. And this is your image eye. A third ray, which is possible, by the way, you don't have to draw it. You can choose not to draw it. Passes through the focal point first until it hits what? Passes through the focal point first until it hits the center of the lens. And then it leaves horizontal. It's basically the mirror opposite of the first ray. If the first ray is a horizontal ray that hits the center of the lens, that goes through the focal point, this one passed through the focal point first, and then it left horizontally. Either way, no matter what you draw, this image should be real, should be inverted, but the size of the image will change depending on where you put the object. Depending on where you put the object, right? So you can either move the object close or farther away. You have 3 cases that you need to memorize. Case number 1, if you put the object very close to the lens, but not beyond the focal point, like not between the focal point and the lens, if you move the object closer, the image becomes bigger and magnified, meaning, and farther away. This is what we use for a projector, by the way, or in the cinema. If you move the object far away from the lens, really far away from the lens and the focal point, the light rays will intersect and give you a smaller image. So the image is smaller and closer. And this is what we use for a camera. Like the whole point of a camera, or a camera's lens, no matter what type of lens it is to take in light from a very large object that's far away from it and squish it down to a very small size so it can fit on the sensor that gives you the image. There's only one case in a converging lens or a convex lens that gives us a virtual image. And that's if you put the object between the focal point and the lens. It's the only case. If you put the object between the focal point and the lens, if you try to draw these rays, this goes through the focal point, this goes through the center, they will never meet. So you have to extend the rays backwards. And if you do, this is just like what you've done in a mirror. The light rays reflect, and then they're extended backwards. Why? To find where the image is. So going back to lenses, if you move the object very close to the lens, between the focal point and the lens, the image becomes virtual and it appears behind the object. This is what we call a magnifying lens. So you put it on top of something, you look through the lens, and you see a much bigger image. This is the only one that's virtual. The rest are real. Very good. Now, one more lens and its application. Instead of a converging lens, we have another thing called a diverging lens, which is called a concave lens. The word to diverge means to move things farther apart. So if you're diverging light, this means that if the light rays are horizontal or parallel, like they were in a convex lens, they move farther away instead. Right? That's why it's called a diverging lens. The rays bend away from the center line, not towards the focal point here, but they always bend so that their extensions pass through the focal point. That's why it's called diverging, moving the rays away from each other and not towards each other. There are, obviously, before I talk about the applications, here's the quick ray diagram for diverging lens, even though you won't really need it still. First, horizontal line from the top of the object to the center of the lens. And then this will bend away or diverge. It will diverge according to where the focal point is. Because even though it's moving away from the center because of the shape of the glass and how it bends, the extension still has to pass through the focal point. Right? Very good. So that's the first ray. Second ray, just pass through the center of the lens. No trouble. Do you see where they intersect? Yeah, you see where they intersect? Here. So diverging lenses do produce an image, but it's very small and it's very close to the lens. It has its applications. All right, so you could say that this thing is diminished or any other description. Then, what's the difference between somebody, last bit, somebody who's long-sighted and short-sighted? People who are long-sighted, not me, can see things very far away, but they struggle with things that they have to look up close, look close at. In other words, they can't see it properly. Now, here's the reason why. When something is really close to your eyes and your eyes are very good at seeing very long distances, that's because the light rays that are coming from the object get focused very far from your retina. If the objects are far away, sure, the light rays meet at your retina and produce an image. If not, however, what do we do? People who are long-sighted, what do we do? We use a lens. Glasses, just a lens. Reading glasses, essentially. What the convex lens does is that it helps the light rays focus all right, at the correct spot. So it's just focusing the light. So since my eyes, if I'm long-sighted, my eyes cannot focus the lens far enough, we need to put a lens in here so it can focus the light for me so that when it hits my retina, I can see clear. The opposite is true for folks like me who are short-sighted. Like I do not see long distances at all. I'm very good at seeing things that are up close with or without my glasses, but I struggle with seeing things far away. If things are very far away, light rays are often parallel. And the problem with my lens, my disc, this lens that's inside my eye, is that it's way too strong at focusing stuff. It's way too strong at focusing stuff. So it doesn't create an image on the retina, it just creates something blurry on the retina. So if the problem with short-sightedness is that they focus too hard, like their eyes are focusing too hard, then what do? We spread them farther apart. We spread them farther apart. So we can give them enough time to focus. So that they can travel a bit further and focus on the retina. So again, How do you correct short-sightedness? You use a diverging lens because you spread it out a bit before they converge very hard. Whereas how do you correct long-sightedness? If their issue is that they don't see things that are up close because their eyes don't focus it fast enough, we pre-focus it for them. So the purpose of the lens, a convex lens, is to pre-focus the light going into your eyes. The purpose of a diverging lens is to just help you understand what is that if my eyes are focusing things too hard, diverging lens diverges them a bit before they go into my eyes. So even though my eyes are like super strong at focusing and they want to focus it here, because they're originally moving away from each other, they focus at the retina itself. Very good. And we are done. Complete. Game over. Anyway, we're done with unit 3. Hope you enjoy the evening. Goodbye.